Okay, so lecture 12 is going to be about beaches, specifically the beaches that are just general characteristics of beaches, but also the beaches that are around Long Island Sound. There's just so many great pictures of lifeguard stands and beaches. This is so funny. But if you think about what a beach is, I think in Connecticut, it's a place where people go to, sit by the water. But I grew up in a different kind of habitat than Long Island Sound. I grew up in Massachusetts and Rhode Island, where the beaches were a place where large waves would hit. And it's kind of, I think, a little odd moving to Connecticut and going to the beach and not seeing any waves. But either way, we're going to start with a general discussion of what beaches are and the different types of beaches that are there, and then move into some of the examples of the biology and ecology that takes place on beaches, because most people look at it again as just an area of sand to go sit on. And we're going to end with some pictures of the different beaches around Connecticut. So in general, there are two types of beaches. The first type is a classic dissipative beach, which is a surfer beach. It has large breaking waves, not close to shore, but kind of offshore. And that's because the waves build up in energy over a very flattish, shallow, sandy subtidal area. It's a very productive habitat. There's a lot of fish, many invertebrates, and lots of diatoms that live in the soil. And then you have reflective beaches, which are very steep. The sediment's a little less sandy and more coarse. There's deep water close to shore, and these are less productive. Now, most beaches in Connecticut are not either one of these beaches. The Long Island Sound is really shallow. There are estuary beaches, which are called spits. Yes, S-P-I-T-S. And spits are known to kind of move around and, change with the weather. Now, if we look at a dissipative beach, this is like the classic surf beach. So you see the land, you see all the white caps from the waves, and you see where the waves start to build. That's pretty far offshore. So if you were surfing, you would start, at that outermost wave, and you can ride waves into shore that way. You can see there's a lot of turbulence, there's a lot of turnover, a lot of oxygen getting pushed into those systems. And you can see even underneath the water just how deep some of those, those wave systems actually work. So when a wave crashes, it pushes a lot of energy underwater, and you can see that with the, grayish discolored underwater areas that are shown in those pictures. So this is just a very classic dissipative beach. And again, if you look at this beach schematically, you can see that the waves build up 300 meters from shore. I mean, that's pretty far. And, they'll build up and start rolling in. And around 100 meters, which is still far from shore, they'll start to crest and actually break. Now, that's very different than this beach that you see here. This is a reflective beach. Now, this beach, you don't really see waves building off the coast. You can see a slightly discolored or darker colored water off the coast, and that's deeper water very close. So what happens here is that the waves don't have a chance to really feel the bottom until they get close to shore. And so they break, and you can see the waves breaking right on the coast there. And then they kind of splash water up into those pool-like areas, but then they quickly, moves back into the ocean. And is it beautiful there? Yes. Is it a place where you can go to, paddle around and kayak and use paddle boards on? Sure. But you better be really careful coming in, because if you surf on those breakers, you're just going to land right on the beach, and that's not going to be too healthy for you. So comparing the two, you can just put those pictures side by side and see just how dramatically different these different types of beaches are. One of the best examples of a dissipative beach in our country is Virginia Beach. I know Virginia Beach is a tourist spot. A lot of people go there to get to the beach. But if you ever go there, again, be really careful going in and out of the water because sometimes the waves break very close to the land. And, I've seen people right on the shore and a wave just coming right in over them. So, there's still, once you get beyond the breakers, you can swim all day. But that means that there's very deep water out there. So here's another reflective beach. You can see that there's not really any waves rolling in off the shore there, but they all kind of, break really close to shore. And you can actually see the depth, see the sand that goes out, and then just beyond the waterline it gets really dark. That drops off pretty quickly there. That's pretty remarkable. So if you look at that similar schematic that we showed for a dissipated beach with a reflective beach, you can see it's deeper. Okay, so there's a lot more sand at the top there, and it builds up, not gradually, but quickly. And so you can see the curves and the waves there, that they break right on the shore. And that's an area on the shore that's called a terrace. And depending on whether it's high tide or low tide. And those areas of white in the figure 2 slides ago, where there's just basically water was pooling, those are called cusps. So, if you ever go to a beach and you see these cusps, you know that, well, there's really deep water out there. And what happens is that when you have deep water close to shore, what that can cause is riptides, and that's that figure with the blue arrows, where it's just going to go to deep water right away, and hence the water is going to move a lot quicker there. Hence it's called a riptide, and anything that's caught in that riptide will just be pushed out farther offshore. It's not really if you're a bad swimmer, you might not want to get caught in a riptide, but on the flip side, all you have to do is swim diagonally out of the riptide, and you'll get to a point where you can slowly work your way back in. So these are common aspects associated with reflective beaches. So if we compare the two, dissipative and reflective, if you look at the outer break zone for the dissipative beaches, you can see that it's pretty far offshore. There's a trough, and then you have this inner break zone, and then you have the beach. Whereas the reflective beach at the bottom there, there's a steep beach face. There's not really outer breaker zones, and those, they break directly on the area where cusps are formed. So then you have on the right-hand side, you can see the cross-section of that. So you see the breakers coming in on the dissipative beach, breaking off the coast, and then slowly building up, slowly towards shore. That's a good surfing beach. Whereas on the reflective beach, you can see that the waves really aren't building up offshore. They build right when they get to the coast, and they break directly onto the terrace. Now, the characteristics of beaches, like I said, most people go to beaches to just go sit, sun themselves, play in the water a little bit. So they're not really well studied. A lot of the ecological factors associated with the marine habitats were done in the rocky intertidal because it's, a 2D habitat. There's not many species present. But what we know at beaches is that there's many organisms that live under the sand. Hence, they're kind of cryptic. They might only come out at low tide. You might never see them if you go to the beach. But if you start digging, you'll get to them. Beaches also help form barriers against coastal erosion. But I think we've all seen with the recent hurricanes that we've had with Sandy and Irene that coastal erosion can definitely take place along beachy habitats, depending on the severity of the storm. They are a very sought-after recreational site. I mean, we're talking millions of dollars a year as far as the total amount of money spent on people that go to the beach, from park fees to gasoline to eating out that day to buying equipment to go to the beach, etc. They are a highly productive detrital food web, so they support different types of fauna, both myofauna and macrofauna that process nutrients. And if you look at that total structure of dunes and beach and sand, they offer habitats for many different organisms. And I know, the shorebirds along Connecticut, the piping plovers, all the different types of shorebirds that are present, they really depend on these habitats for, nurseries and grounds to capture prey, as well as migratory patterns. Now, there is a difference between beaches throughout the year, and if you look at the summer and winter beach, in the summer the sand builds up on the beach, and you end up with this nice berm that's present in the summer. And in the winter, the storms change. It's kind of just a different function, and you have the sands get pulled off the beach. Basically all the sand gets moved farther offshore, and you can produce like a sandbar offshore. But it also, a lot of times you go to the beach in the winter, you see a lot more rocks, a lot more boulders that weren't there in the summer, but they were there. They were just buried by sand. So, sand, definitely moves, especially in Long Island Sound, because most of the beaches here are spits. So, throughout Long Island Sound, you might think, when's the best time to build, a house on the beach? Well, it would be in the winter when there's not a lot of sand that's going to get pulled away. That way you have a good base to build on. And you'd be surprised how many people still build at the wrong times of year. So if we look at some of the primary producers at beach zones, you have diatoms that I mentioned already. Those are just some of the different species of diatoms that are present there. And what's really unique about these species is that they have a specialized behavioral characteristics that allow them to really thrive in the surf zone. They have a very stable population structure because they live in faunal most of the time. But they have this unique diurnal migration. And that means it happens every day, and it includes the sand and the water column. So in the morning, they rise up, in the sand. They actually come to the sand. They kind of rise, get to the surface, and as the water waves over them, they attach to any kind of air bubbles that might be present. They're carried out, via waves, and this is where they form those foams that, you see. So they reproduce out there. A proportion of them leave sediment, and it depends on the kind of the wave height that might be present. And in the afternoon, they sink back in, and they develop this kind of mucousy, morphology, and they're carried offshore with, with just the waves. So they have this morning rise up, afternoon sinking that takes place that allows them to stay not only in the water column but close to the surface of the sand and just subtidally. That allows a lot of different organisms to feed on them, etc. The other producers in the habitats are the seaweeds that, if you think about when we went out to Lighthouse Point Park, I showed you the wrack and all the seaweed that was in that wrack. Well, depending on the beaches that you go to around New England, the wrack could be several yards thick and a good yard or two deep. So you could start ripping through that to see all the different producers that might be present. So there's, in general, two types of consumers in these habitats. So there's both the surf zone consumers and the intertidal sandy beach consumers. In the surf zone, you have plankton and, different shrimps, different polychaetes, different amphipods. And these also have a normal horizontal and vertical migration taking place. And then you have some benthic animals like quahogs and clams and different fish that live there that might be eating the producers as well. And then in this intertidal sandy beach part, you have all different types of marine invertebrates, from worms to crabs to bivalves. So most times when you go to the beach and you're sitting on a blanket, chances are you're, sitting on most of these things and you don't even know it. The other thing too is if you go to some beaches, this is a beach down in Milford, this is the Audubon Society, and you see all these odd looking, they kind of look like, a lot of dogs who were let loose that had to go to the bathroom really bad. But those are the same kind of wormholes that we talked about when we had the flow lecture. So they burrow out these holes, and there's an entrance and an exit. And some of these worms can be quite large. And when the tide comes in, you can they usually get knocked down, but you can see these kind of tubes sticking out. And these tubes are tube worms. They infaunal, they're just waiting for prey to come by with the incoming tide so that they get enough food to eat. And to show you how large they can get, this is just one marine polychaete that's lived in the soil, and that's probably around 12 feet in length. They're not snakes. They're not going to come out and grab a human or anything close to that. They're just living inside their tubes waiting for organisms to come through that they can capture and feed on. And obviously the organism there just had a really good habitat to live in. So these polychaetes can be quite large. If you're ever looking for a bait to go fishing, is another perfect example of where to go. Just find a beachy area, look for those telltale signs that tube worms are present, and start digging. So if you look at the zonation pattern that might be on a sandy shore, you can see that there's the outer turbulent zone. And that outer turbulent zone is, might have some weak bottom currents associated with it, but there's some amphipod species that might be out there in the soil. And then if you remember what happens to waves in shallower waters, well, they start to feel the coast, and you can see the point break there where the waves kind of build up. You have a transition zone where there's a lot of strong wave energy, and you might have some of that surge associated with bottom currents. And then you have the infralittoral or the surf zone where there's a lot of wave energy, a lot of bottom currents, much surge in those habitats. And you can see there's a whole plethora of organisms that live right in the water or right in the soil close to that. And then you have the mid-littoral zone that gets damp with the wash that comes up via the wave energy and the set of organisms that live there. And the superlittoral zone that includes like the dry sand, where the fauna are air-breathing crustaceans or insects like amphipods or crabs. So, a lot of people go to the beach, they don't really see this as, something that's alive and it's a very dynamic habitat. But when you take a cross-section of it and you look at and compare the outer turbulent zone all the way through the superlittoral zone, you can see there's a lot of organisms present at the beach every time you go. Now, the other thing that beaches are famous for, especially in Connecticut, are the dam birds. And there's sandpipers and plovers and herons and ducks and raptors and terns. There's all different types of, mostly semi-endangered species of birds that utilize the Long Island Sound as habitat, as nesting areas, and as for migratory, patterns. And, Connecticut has a very large birding history. This our own Department of Biology had Noble Proctor, and I would urge you to just Google his name. Noble was probably one of the world's best ornithologists, and as such, he had the Great List and, traveled around the world looking for different bird species, and is, fairly famous in Connecticut for having the largest bird list, of the local ornithology societies. So look him up, Noble Proctor. So one of the benefits that we get from beaches is the fact that it's a coastal barrier. And those dunes actually help, our towns and our cities. So they're formed by a balance of wind and erosion and water currents. Now, most of the beaches in Long Island Sound I mentioned are inhibited by the absence of wind and wave action, only because you don't really have enough fetch or area for waves to really build up between Long Island and the coast of Connecticut. So the beaches that are present in Connecticut are these spits. And you can see different spits around the state. They develop. They may move around. What you see is beach. One area, might not be beach the next area. It might get smaller. It might get larger. It all depends on wind, erosion, and the water currents that are present. Now, coastal habitats can be harsh habitats because the soil depends on whether or not, what the bottom's like. You can have sand on sandy beaches, and you can also have quartzite, gravel, or you could have beaches with both. For your semester project, you're going to do the Hammonasset, hopefully, or any other habitat that actually has a sandy beach and a cobblestone area. On the cobblestone area, you're going to find many different quartzite gravel, and it's going to look kind of like the rocks in this picture. Those soils can be very acidic, though they can be very well drained as well. And you can have huge temperature changes over the soils on a daily basis. If you think about the tide just going out and the soil stuck in a particular habitat, it's going to get warm over time. And in the sands, you're going to have unstable, plants that have to rapidly adapt. Because if you're a plant that decides to, germinate in, sands, you better be able to deal with life in a harsh environment. So I put these next slides in just to give you some examples of some very unique beaches. This one is not in Long Island Sound. This is a typical dissipative surfer's beach. This is Second Beach in Middletown, Rhode Island. It's several miles long, absolutely beautiful beach. The waves pull in pretty far offshore, and you can surf all the way in. Just a really, really beautiful habitat. So the next couple are going to be in Long Island Sound. So this beach is in the Eastern Sound. It is in Ocean Beach in New London. And this is probably the most ocean-related beach in Long Island Sound, even though the salinity between the Ocean Beach that you just saw in Middletown, Rhode Island, and Ocean Beach in New London is drastically different from one another. Ocean Beach, New London, the salinity is going to not be, true seawater. It's going to be probably in the mid, maybe low 30s. But, no denying, it's just a beautiful habitat. It's got some rocky outcroppings in it. It's not a beach you can surf at. It's not a beach you can really boogie board at either because there's just not a whole lot of waves. Now this one is one that you might know or be familiar with. This is Hammonasset State Park in Madison, Connecticut. And this is a really long beach too. This goes on for a few different miles. This is the westward facing part of the beach. And if you look at how close the breaking water is, the waves there are to that boardwalk that's present. So a few years ago what they did was they did a restoration effort where they brought in a barge that basically threw sand. So it picked sand up off the coast and they just blasted the sand onto the beach. And they did this all day long for several months until now you have this much wider sandy area present. And that's important because as these waves build up, come close to shore, and they crash, they pull sand out with them, especially in the winter. So usually every spring they do an assessment to see, do we need to replenish the beach? Because if they don't replenish that beach, at some point that boardwalk's going to be gone and that building will start being compromised. So this is another beachy area in Connecticut. This is Silver Sands in Milford. And there's the island off there that at low tide you can walk to, but nobody lets you walk into it anymore because of the birds and the nesting areas that might be present there. And it can actually get kind of dangerous as the tide comes in if you're walking back. So, this is just another example of a Long Island Sound beach. Again, the absence of waves is obvious. Now, this last beach is Sherwood Island. If you remove that kind of fir tree and the dead branches in the foreground, and you looked at that area, I mean, that's It just looks like a typical tropical Caribbean beach that somebody would just go walking on. It's absolutely beautiful. But you can see in that picture the rack line. You can see that line, and it's kind of dark along the beach, right where the high tide mark would be. So this is the tide's probably going out here, and you can see a little bit of the white caps there close to shore. So, you should be able to describe the two different types of beaches, how they differ, explain to me how waves differ based on the beaches that are present and why that is. Talk about the general producers that are present, the consumers that are present, as well as the that cross section of the beach, comparing the outer turbulent zone to the higher zone and the terrestrial habitat. So there's plenty to go through on this lecture, and the idea is that the beaches in Long Island Sound are spits, and they're not really affected much by waves.